Okay, probably let us start. Today, we have a session, example problem of discrete geometry, and our first two speakers from Japan. This our old friends, and Hiroshi Nozaki start from first talk, few distant sets, and the Dodecahedron conjecture. Please start. You have 30 minutes. Okay.
Okay. Yeah, thank you for the introductions. And I'd like to thank organizers for giving an opportunity of this talk. And I'm very happy to talk here. So I will talk on some location of finite sets in Euclidean space. So few distance sets. And we introduce the dodecahedron conjecture about few distance sets. So let's start with a simple example and the definition of S distance set. So S distance set, let X be a finite subset of the Euclidean space of dimension D, and D denotes the Euclidean distance. The set A of X is a set of Euclidean distances between distinct points in X. X is called an S distance set if the size of A of X is equal to S. This is a quick example. So regular pentagons, the vertices of regular pentagon has two distances, namely, so one is H and diagonal lines. So regular pentagon is a two distance set. So main problem for S distance set is to determine the largest possible S distance set in RD, or the unit sphere SD minus 1 for given S and D. This is the regular dodecahedron D. So actually, the regular dodecahedron is 5 distance sets. So this is the dodecahedron with edge length 1. So we have a regular pentagon as face. Regular pentagon has distance 1 and tau. Tau is the golden ratio. And the cube in the regular dodecahedron. So cube has 3 distances, tau, the square root of 2 tau, and the square root of 3 tau. Now, the square root of 3 tau is the diameter of the circumsphere. And we can calculate the second largest distance, tau plus 1. So A of D, namely the distances of the dodecahedron, is 1 tau, the square root tau, tau plus 1, the square root 3 tau. So the dodecahedron is 5 distance set in R3. The dodecahedron conjecture is that the largest 5 distance set in R3 is the regular dodecahedron, and it's unique. This was a long-standing open problem, at least for 25 years. So in this talk, we will introduce a proof of sketch of dodecahedron conjecture. And next speaker, Masashi Shinohara, will talk the proof of the dodecahedron conjecture in details more. Okay. So now we introduce absolute upper bound for S distance set. So we have natural upper bound for the size of S distance sets. So-called absolute bound. Bernstein proved that if X is an S distance set in RD, then the size of X is at most D plus S choose S. And Gotthard-Sider proves that if X is an S distance set in the unit sphere, then the size of S distance set is at most D plus S minus 1 choose S plus D plus S minus 2 choose S minus 1. Recently, Petrov and Pohata gave a new simple proof of the absolute bound for Euclidean case. Very roughly, we consider a polynomial function with D variables. So, and we make these functions. actually, this is a polynomial function of degree 2s. So then this means the linear space of polynomials of degree at most 2s with d variables. Then we have actually fx of y is the identity matrix, and the rank of fxy, this is a matrix, fx of y is equal to the size of x, and they proved that the rank of this matrix is at most these dimensions. So the dimension of the linear space of polynomials of degree at most s with d variables. Yeah, this proof is very simple actually, and yeah, this inequality is proved by some theory of quadratic form. Actually, the proof of Banne-Staton is a little bit complicated, but this proof is very simple.
What is dim S? Dim S, what does it mean?
Yeah, this is the dimension of the linear space of a polynomial function of degree at most s with deep variables. What is exactly Deta's S chooses? Is it okay?
Okay.
Okay. Okay, please interrupt me if you have any question. Okay. Now we introduce the concept of S-coloring. So XR is called an S-coloring if X is a finite set and R are disjoint binary relations on X. And R0 is the diagonal relation of X, and Ri's are the decomposition of X by X. So to S-coloring, XR and YT are equivalent if there exists bijection. F and G, F from X to Y, and G is 1 to X, from 1 to X to 1 to S, such that XY is in Ri if and only if Fx and Fy is in TGI. So very roughly, so there has the same graph structures, and we can permutate colors also. So relation matrix AI is a matrix indexed by the set X, and whose XY entries is 1 if XY in Ri and 0 otherwise. So for constructing an S-distance set, we would like to find some real numbers AI such that this matrix is a low-dimensional Euclidean distance matrix. So from S-coloring, we would like to construct a S-distance set. So in particular, an association scheme is very good S-coloring. So association scheme, XR is an S-coloring. Let AI be the relation matrix of Ri, and the coloring is called an association scheme of class D. If the algebra spanned by AI over the complex numbers is an algebra. Moreover, an association scheme is said to be commutative if I is commutative. Here, so the multiplication is the usual multiplication of matrix. So if an association scheme is said to be symmetric if AI is symmetric for any I. So this is an example. So let G be a finite group, and Ci is a conjugate class of G, and we define the relation Ri like this. So the set of X, Y such that there exists C in Ci, such that Cx is Y. Then GR is commutative association scheme. This association scheme is called group association schemes. So from finite groups, we can construct a lot of association scheme. And in this meaning, so we say an association scheme is a combinatorial, some combinatorial generalization of finite groups. From this association scheme, we can construct an S-distance set which has the structure of association scheme. So if XR is a symmetric, we need this assumption of symmetric association scheme. Then R has primitive idempotence because the Bose-Messner algebra. So this algebra is called a Bose-Messner algebra. The Bose-Messner algebra is semi-simple, and there are primitive idempotents. So actually, EI is a orthogonal projection matrix into the same eigenvalues of AI. So AI is positive semi-definite, and EI is in the algebra R. So EI can be expressed by the linear combination of AI. And now AI is in real. So EI is an S-distance set in the unit sphere because we have A0 is the identity matrix, and the diagonal entries are the same. In the unit sphere, for where this dimension D is the rank of EI. So from association scheme, symmetric association scheme, we can construct lots of S-distance sets. Okay. So for an association scheme, so character table is important to check some information. So now AI can be expressed by another basis, EJ. Now Pij is actually the eigenvalues of AI. The EI can be expressed by the linear combination AJ. Oh, excuse me. P is the matrix. P is a matrix whose ij entry is Pji. This matrix is called the first eigenmatrix or character table of an association scheme. So essentially, if an association scheme is a group association scheme, then essentially this character table, the first eigenmatrix, is the same as the character table of finite groups. And Q is called the second eigenmatrix. So here, now we can regard EI as the gram matrix over some subset of the Euclid of the unit sphere. So Qij, essentially Qij is the inner product. So namely the distances of the finite, this embedding. So we have this relation PQ is essentially the identity matrix. So from P we can calculate Q. So actually the dodecahedron has the structure of an association scheme with a natural relation Ry, namely xy, such that the distance over xy is equal to AI. AI is the distance of the dodecahedron. Then we can calculate the second eigenmatrix Q like this. So this column, the first entry 3 means the dimension of the embedding. So these are in a product. Actually, this part corresponds to the dodecahedron. We have another representation of 3-dimensional. Actually, this is also the dodecahedron. So, and now inner products, the difference of inner products are this part. This means that so the graph A1 is isomorphic to the graph A4. Yeah, we have two embeddings. There the dodecahedrons. So now we introduce examples attaining the absolute bound quickly. So for an S distance set is said to be tight if the S distance set attains the absolute bound. Non-trivial tight S distance set is this next distance set is not only non-trivial tight S distance set. This is in 8-dimensional distance set. And for tight S distance set X, X has the structure of an association scheme actually. So then for S is equal to 2, the tight 2 distance set has the structure of a strongly regular graph. A strongly regular graph is an association scheme of class 2. So they are good strongly regular graphs. From the structure of an association scheme, we can prove the non-existence of tight S distance sets for S is at least 3. So these are a list of largest S distance sets that does not attain the absolute bound. So like this, in particular, so for S is equal to 2, for almost all dimensions, we can determine the largest size of S2 distance set. Actually, D plus 1 choose 2, that's the embedding of Johnson association scheme. So finally, gradually you solved this one. Yeah, that's a very good result. So for spherical S distance set, we have several main tools to determine the largest S distance set. First, we have a lot of good representation of an association scheme, and we have several bounds, so-called harmonic absolute bound, linear programming bound, or semi-definite programming bound. For given inner product in the set, so we can give a good upper bounds like this. So good S distance set example. We have good example of S distance set and good upper bound. We can determine the largest S distance set. So on the other hand, so largest S distance set RD, the situation is different from the sphere. So first, for S is equal to 2, Resonex proves like this. This number means the maximum cardinality of non-S distance set. The asterisk means we can determine the largest S distance set. So this table comes from this paper, Szöllősi-Östergård. So for S is equal to 2, by classifying of graphs such that the graph can be representable as 2 distance set. So he gave good computer algorithm for classifying graphs whose has a representation of a S2 distance set. And so for S is equal to 3, and in 3-dimensional, 3 distance sets in R3, this is the largest 3 distance set in R3 is the icosahedron. This is also interesting result. So this is proved by first Shinohara. He's the next speaker. And Szöllősi-Östergård gave some algorithm to classify S colorings, which has a representation of S distance set. So their algorithm kind of extension of Resonex1. So main tools to determine the largest S distance set in Euclidean space is first geometry in low dimensions and computer algorithm for classifying representable colorings. So an idea in Szöllősi-Östergård. So now we've fixed dimension D. So we would like to find the S distance set in RD. So we can make we can make a matrix D. D is like this. So this corresponds to the distance matrix, but xi are variables now, and by normalization, some normalizations, xs is, we may put xs is 1. Now we can construct matrix M like this. Dij means the ij entry of D. So this M is the ground matrix of this distance matrix actually. And we have to check the rank and positive semi-definiteness. So if M is the ground matrix in D-dimensional Euclidean space, then all D+1 times D+1 submatrices of M has rank at most D. So then we can calculate the Graebner basis B of this system. So for any N, so they determine N and this equality. If this polynomial is equal to 0, then xi and xj are different. So if B is 1, then we have no solutions of this system, then D has no representation in RD. If B is not equal to 1, then they have then may have a representation in RD. Then we have to check the existence of real positive solutions. We can reduce a lot of metrics which cannot be representable in D dimension. So the Dodecahedron conjecture, this is the main result of this talk. So the largest five distance set in R3 is the dodecahedron, which have 20 points. So idea of proof roughly here. So first, we prove some existence of S prime distance subset X in large S distance set. This is a kind of Ramsey type problem. So for large S distance set, we have a kind of good S prime distance subsets. Usually S prime is less than S. So originally Ramsey problem is there are large cliques or co-cliques in large graphs. Yeah, that's the same type of problems. First, we prove some existence of S prime distance subsets X, actually relatively large X. And by the method Szöllősi-Östergård, as we introduced, by using their method, we can give graph augmentation algorithm from X. So we can determine for this S distance set, we can determine whether we can add a point to X while maintaining S distance set. So, and third, properties of certain subsets of the dodecahedrons. So we give some geometry, and that can reduce the computational cost. This second part. Yeah. In particular, first result is very good and important. This first result reduce much computational costs of this second part. So therefore, this is a key result, theorem 5. Every 5 distance set in R3 with at least 20 points contains an S distance set for some S. S is at most 4 with 8 points. This is key result. So by this theorem, we can reduce much computational costs. So this theorem is very important. So next speaker, Masashi Shinohara, will talk this theorem in details. Oh, yeah, we don't have much time. So
yes, you have, please, maybe try to finish or just to take some time from Shinohara.
Okay. Yeah. So now we introduce some property of subsets of dodecahedron have same graph structure. This means having the same the structure of colorings. This E1 and E2 are the dodecahedrons, and ret 5 is a Galois group of Q, the square root 5 over Q. So, and phi hat M is defined by like this. Then phi hat is an automorphism of the Bose-Messner algebra R, such that the image of EI is E2. Then let M be a simple principal submatrix of EI, E1. So then M is identified with the subset of the dodecahedron. Then M and phi hat M are identified with subsets of the regular dodecahedron, and they have the same coloring structure. So actually, so phi hat can be expressed by permutations of vertices. For example, so 1, 2, 3, 4, 5. 1, 2, 3, 4, 5 is a regular pentagon. And the image of this is 1, 16, 10, 7, 19. 1, 16, 10, 7, 19. This is also regular pentagon with edge distance is second largest distance. So now we can switch the distance A1 and A4. So these two subsets has the same structure of colorings, but the distance is different. And there exists a unique 3-distance subset of a regular dodecahedron with 8 points up to isomorphism. The subset is a cube, lemma 8. There exists exactly 116 of 4-distance subsets of a regular dodecahedron with 8 points up to isomorphism. And there exists only 63 full colorings that can be representable as 8.4 distance subsets of a regular dodecahedrons. So 53 in 63, 53 colorings, 53 colorings has two representations as 4-distance set in the regular dodecahedron, and 10 colorings has only one representation in one representation as 4-distance subset in the regular dodecahedrons. Actually, okay, we can skip the outline of the proof, but anyway, we can count without classifying the colorings. We can count by band-size lemma actually. Okay, this is the last slide summary. So main result is the dodecahedron conjecture. So the largest 5-distance set in R3 is the dodecahedron. And the key theorem is that every 5-distance set in R3 with at least 20 points contains an S-distance set for some S. So S is less than 5 with 8 points. So about this theorem, so next speaker Shinohara will explain in details. So sketch of proof, correct all coloring with 8 vertices that can be representable as a S-distance set in R3, and only 64 colorings in them can be subset of 20.5 distance sets by computational method obtained by Szöllősi and Östergård. Actually, this 20.5 distance set is uniquely determined from a given coloring. And this number 64 is the number of such colorings in the dodecahedron. Then, so we can prove the uniqueness of the largest 5-distance set, and it's the dodecahedrons. Yes, thank you. Okay. Thank you for listening.
Thank you. Yeah, thank you very much. It's interesting introduction and some of the review, and as well as the review of the proof. But actually, we have no time for questions. I don't
Okay.
know. Yeah. You can maybe we will have question after the second presentation.